Now I will speak about the analysis of the eye tracking data in order to extract the information about the changes in pupil area and to understand if the conditions of our interest do differ between each other according to objective statistical criteria. The first part of this section of the tutorial will be dedicated to the pre-processing of the eye tracking data, in particular to the procedures related to artifact detection. Then we will cut the epochs around the events of interest, and finally we will compute the statistics about the differences between the conditions. And we will start from artifact detection. But before detecting any artifacts, we will have to extract the data from the EDF file, which is recorded by the eye tracker. In order to do this, we can use EDF to mat function, which is freely available online. I guess there are many other tools to extract the time series of the pupil size, but we use this one at the moment. First, I will show you a number of slides and figures and try to explain in general which are the stages of the artifact detection. And then we will go through the MATLAB script step by step, and we will try to realize the analysis of the artifact detection procedures. We are going to deal with two time series: the pupil size for one eye and the other, the right and the left, and the time of the samples, which is stored in the structure as it is shown here on the slide. Of course, we also need to know when exactly was the onset and the offset of the stimuli. In our case, the stimuli were the gray squares shown on the screen. One of them was brighter and the other was less bright. The events are also stored in the structure obtained from the EDF file. In the info substructure, you can find the name, which was either start stim or stop stim, as it was programmed in the PsychToolbox script, which we used for the task. And the timing of each event of interest, the start of the stimulation and the end of the stimulation, is stored in the field time of this structure. So we run the loop across all the events, and if the name of the event corresponds to the names which were given by us, which were encoded by us, we extract the time for the onsets and the offsets of each event. Now we don't yet speak about the conditions of interest. We are going to extract the onsets and the offsets of all the events. Now when we have the series of the onsets and the offsets, we can easily plot them in the shape of those vertical lines on the original time series of the pupil size variation. And it is pretty easy to see already that after each onset there is a constriction of the pupil because the stimulus which we show was brighter than the background. And here we plot the offsets in red. The interval between the black and the red, this is the duration of the presentation, the stimuli. And as you can see, the response to each presentation starts somewhat later than the onset, and it recovers already after the offset of each stimulus. So here I zoomed on two responses so that you can better see that there is really a classical sluggish time series. Now this is the time in seconds, and the exposure time was roughly 1 second each time. So now we are going to speak about the artifacts. The artifacts, they mostly come from blinks. When the eye closes down, the detected size of the pupil also goes down, literally to 0. And there is a beautiful algorithm of multi-level detection of the artifacts in the pupil size recording, created by Mariska Kret and Elio Siak-Skie. The scripts are mostly in MATLAB. They are available online, and I based my analysis on this pipeline with some modifications and simplifications. Of course, there is no perfect strategy, but these guidelines can help you to build your own strategy which is optimal for your experimental paradigm, and which helps you to clean your data as much as possible. This is an illustration from the paper of Dr. Kret. You see the evolution of the blink, single blink, and you see that the exposed size of the pupil goes down. And this is the time series, and you see that in both eyes there is an interruption and a trend for reduction of the size, a rapid reduction of the size of the pupil. In this case, it is diameter. In our recording, it is in pixels, since we take the area of the pupil. Here you can see another illustration from their paper, which shows and explains 3 different options to identify the artifacts, the samples which should not be used in further analysis. First, you see that the speed, the instantaneous variation of the speed of changes in pupil diameter is too high. Typically, the pupil size is changing pretty slowly, since it is related to the autonomic activity and the contraction of the smooth muscles. They cannot be as fast as the skeletal muscles, strict muscles, which drive, for example, our blink. So, if the speed of changes in the pupil diameter is much higher than what typically happens, then those samples should be rejected or considered to be artifacts. The other approach is to compare the current amplitude of the pupil diameter and the smooth baseline, which is estimated with the help of the low-pass filter. As you can see, most of the points, they don't differ much from this smooth baseline, while some points, they are really different from it. And those points which stand aside of this smooth baseline should also be considered artifacts. And finally, if a short sample, short recording, is separated with important gaps from the rest of the recording, it is just very hard to understand if there was a smooth strand or not. It can be perfectly well, but it also can be an artifact. In this case, for the sake of the accuracy and to be sure that we don't grab any artifacts, we just reject those small islands as well. So, to summarize, we have 5 stages of the artifact rejection or artifact detection procedure. And we go one by one. First for one eye, then for the other eye. First, range filter. This is the most basic approach. You just set a certain threshold for the minimal acceptable and the maximum acceptable pupil size, which appears reasonable to you, and everything below and above considered to be artifacts. Very simple, very basic. Then the dilation speed filter. You estimate point by point the dilation speed, velocity of the changes, and if this velocity is too high, you reject the samples. Deviation filter, first you estimate the smooth baseline, and then the samples which are too distant from this baseline are considered to be artifacts. Isolated sections or isolated islands filter estimates the gaps, the C's in the recording, and the islands which are too small are rejected by us. And finally, the gap padding filter is a simple approach which removes a certain number of samples at the border of the gap, just to be sure that we don't grab any changes related to the onset, initial phase of the blink, which is unlikely to be related to the experimental task in most cases. everything related to blinks should normally be excluded. Now let's see the example of our data sample and the illustrations of what is considered to be the artifacts, which points are considered to be artifacts and which stay after the rejection procedure. In red, you can see the samples which are qualified as artifacts. This is a range filter, and everything below 100 pixels of pupil size is considered to be artifact, and obviously those samples are artifacts. Now the second stage, the dilation speed filter. In black you see the points which has been rejected at the previous stage or stages. And in red you see what is filtered out at this stage. And here we zoom in. Maybe here the criteria must be more liberal to include those points as well, but quite a lot of points with a rapid dilation or constriction, the absolute values of the speed of changes, which is too high, are rejected by this procedure. The deviation filter finishes the job. Now you see in red what is rejected by the current stage of the analysis, and obviously what survived the dilation speed still is detected by the criterion of the deviation from the smooth bias line. The next filter removes isolated islands, not a lot, but some parts which might be a good recording still are removed and rejected. And the gap padding, it removes 50 samples each time around the gap, so that the initial part and the final part of the perturbation related to the blink is removed as well. And then you decide if you use the information from both eyes or only from one eye. The decision is based on whether there is a large difference in the quality of the data in one eye and the other eye. If the difference is important, then you use information only from the eye which gives you the best quality. If the difference is just few percent, then you average up the signal recorded from the two eyes, which gives you a better signal. And in the parts of the recording which corresponds to the gaps, to the artifacts, you interpolate the data. I personally prefer to use cubic interpolation, but maybe spline or linear is good as well. Anyway, at the stage of further processing of your data, when you have the epochs related to the events of interest are extracted, you might considering consider rejection of some epochs which have too many artifacts, or in other words, an important proportion of the data samples spoiled or identified as artifacts. Then those epochs should not be used in further statistical analysis. This is the consequence of the data processing steps, and here I indicate in red the parameters I used in my protocol for each filter. So for the range filter, it is from 100 to 4000 pixels, which is pretty liberal. For dilation speed filter, I used the maximum instantaneous dilation or constriction rate at the level of 5 pixels. The low pass filter filters out everything faster than 16 Hertz. And then the deviation from this smooth line, smooth baseline, which is considered critical, is 5 pixels as well. Finally, the islands are considered to be islands if they are separated with more than 40 milliseconds and which have a size of less than 50 milliseconds. We eliminate only the small islands. The large islands are considered to be useful for us. And now the gaps are considered to be gaps if they vary between 50 and 500 milliseconds. And the padding window is 50 milliseconds, both backwards and forwards. Yeah, and now we will go to the data processing in MATLAB to see how it works and what is the code at each step. And we will see the outcome, which comes immediately after each stage of filtering.